Hey friends, welcome to our video lecture on topic 10.1 Organic Chemistry Fundamentals. So just a big FYI here, this is a lot, and so definitely pay attention to how you're feeling. I highly recommend that you watch a little bit of this video and then take a break and then watch some more and take another break. It's a lot. Our objectives for today, we're going to define homologous series, we're going to define structural isomers, we're going to talk about the names of functional groups and then the classes of organic compounds that are related to those functional groups. We're going to talk about how we name organic compounds based on those functional groups, and then we're going to wrap up with a little look at classification of primary, secondary, tertiary, and even some quaternary organic compounds. So our essential idea for today, organic chemistry focuses on the chemistry of compounds containing carbon. And carbon's pretty cool. So I've got a little bit of a Bohr model up here where we have those 1, 2, 3, 4 valence electrons. Remember that we have that octet rule that says that a full valence energy level is really the most stable configuration for atoms. Carbon has 4 electrons. It can make bonds with 4 more things of electrons, which means that carbon has a lot of flexibility in how it bonds to stuff. And originally, this idea of organic chemistry was based just on the chemistry of our compounds that are formed by living organisms like us. But then there was a guy, Wöhler, and he made urea, which is a part of urine, but he did it without urine. And it was very exciting and changed a lot of organic chemistry. But organic chemistry is still a lot of the chemistry of the compounds that are made by living things, but we also have learned how to make a lot of those compounds in the lab, not only in living things. Another cool idea related to the chemistry of carbon is this idea of catenation, which simply is that carbon can make lots of long chains of itself. So we can take carbon and add it to more carbon and bond it to more carbon and another carbon and another carbon. If I try to do that with hydrogen, hydrogen only has an s orbital. It can only have 2 valence electrons before its energy level is full, and so you kind of get stuck here. Like H can bond to H and that's the end, whereas carbon can make these crazy, crazy, crazy long chains, and this is the idea of catenation. So welcome to organic chemistry and carbon chains of carbon. So the first thing we're going to look at is this idea of a homologous series, and homologous series are simply groups of organic compounds that have similar structures, and they vary only by CH2 groups. We call these methyl groups, CH2 groups. So this is an example of a homologous series. It's the alkane series. And first up, I've got methane, which has 1 carbon. There's only 1 carbon here. Here it is. Ethane is the next guy in the series. We're literally adding 1 carbon and 2 more hydrogens. So I had C and 4 H's. I'm going to bust in here and put a CH2 and then throw that hydrogen on at the end. We're going to do that again, add another CH2 and another CH2 and another CH2. So the only thing that we're changing is the length of these carbon chains. We call these homologous series. What's kind of cool is that there are patterns in their properties. So imagine that we're looking at this alkane series, this alkane homologous series. They all have single bonds between the carbons. They all have single bonds between the carbons. There are no branches on any of these carbon chains. What do you think is going to have the highest boiling point? What do you think is going to have the lowest boiling point? Did you guess that the lowest boiling point is methane? We have to get this guy down to negative 161 degrees Celsius to make it a liquid. Anything above negative 161 degrees Celsius is going to be a gas. Negative 89 Celsius for ethane, negative 42 Celsius for propane. Just about freezing point of water is where butane will go to a liquid. And then pentane, we can get it to liquid gas. That boiling point is super close to human body temperature. So human body temperature is 37 Celsius. So that's about the same temperature that pentane goes from a liquid to a gas. So the more carbons we have, the higher the boiling point. the reason is this. So there are lots of electrons all around all of these compounds. You have all these electrons zooming around the orbitals of all these compounds. And pentane has more electrons, which means that it's going to have a greater London dispersion force. So that intermolecular force, London dispersion force, is greater because there are simply more electrons flying around this molecule than around this molecule. We can take advantage of that with this idea of fractional distillation. So this is how we manage crude oil when we distill our crude oil. So we pump all kinds of stuff into these heating burners, and then the guys with the highest boiling point are going to zoom up to the top. Guys that have pretty low boiling points are going to stay down here at the bottom. And so these guys with boiling points 300 to 370 Celsius, they're going to get pulled out at this level. And then things that don't need to be quite as hot can get pulled out here. Things that less hot. And then here we have the coolest of our organic compounds, these alkane series. So our petroleum gases, methane, ethane, propane is going to get pulled out at these lowest of the low temperatures because their boiling points are the lowest compared to the other guys. So this is how we purify, distill out, refine, if you will, our oils at those oil refineries that we have all around Houston. All right, how do we represent lots of organic molecules? So we can draw some Lewis dot structures to show organic molecules. So remember that Lewis dot structures are going to show the valence electrons that are in the bonds around molecules. So carbon has 4 valence electrons. There are 3 of them. That makes 12. Hydrogen has 1 valence electron. There are 6 of them. That makes 6. 12 plus 6 is 18 total electrons. So I'm going to do C, C, C. I'm going to throw some H's around. I have run out of H's, but that's okay because here's what's going to happen. If I do 2, 4, 6, 8, 10, 12, 14, 16, 16. Uh-oh, I only have 2 more electrons, and I definitely need some more bonds. But if I make a double bond here, everything is golden. So this is the Lewis dot structure for propene C3H6. We can also represent organic compounds with our empirical and molecular formulas. Empirical formula of dinitrogen tetroxide. I'm actually going to write the molecular formula first. Di is 2, tetra is 4. So this is the molecular formula. To get to empirical formula, I need to reduce it to lowest terms. Divide both sides by 2 because that's the least common multiple of 2N4, and N1O2 is going to be the empirical formula. N2O4 was the molecular formula. We can also represent our organic molecules with different kinds of structural formulae. We can look at the full structural formulae, and that's what this is. It's showing all of the atoms and all of the bonds between all of the atoms. We can use a condensed formula where I'm not showing those lines for the bonds. I'm just listing out the groups of atoms. CH3 is going to look like CH3. CH2 is going to look like this. This CH2 will look the same, and then CH3 will look that same again. And so we can go from that condensed formula to that full structural formula pretty easily. The last one, super convenient because there's so little to it, but sometimes a little bit confusing to read, are the skeletal structures, these guys. So what happens is this, each one of these vertices is a carbon, 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 carbon. And then we are working on the assumption that all the hydrogens that are needed to fill up the valence of carbon to get to that octet rule are there. We're just not drawing them. So this carbon only has 1 bond right now. That means that there must be 1, 2, 3 hydrogens around it because we need to make 4 bonds to get carbon to 8. This carbon has 1, 2 bonds on it right now, so I'm going to assume that there must be 2 hydrogens on it to get it to 1, 2, 3, 4 bonds, because 8 is great. Same for this guy, and then this carbon again only has 1 bond, so there must be 1, 2, 3 hydrogens around it to get to 8 is great. Good? Good. So let's look at some nomenclature. This is our fancy word for naming things. So the rules for naming compounds are made up by IUPAC, the International Union of Pure and Applied Chemistry. So anytime you see something that says the systemic rules or IUPAC rules for naming things, this is who IUPAC is. They meet every once in a while and make the rules for naming compounds, and we follow those rules. And the most important rule for naming things in organic chemistry is to count the carbons. We do love to count our carbons in organic chemistry and biochemistry. This guy has 1 carbon. Our prefix for 1 in organic chemistry, which is different from when we did covalent compounds, our prefix for 1 in orgo is meth. So I have 1 carbon, I have 0 double bonds. I'm going to call this guy methane. This guy has 1, 2 carbons. My prefix for 2 is eth. It's ethane. Remember that in these skeletal structures, each of the vertices is going to be a carbon. So I have 1, 2, 3 carbons. 3 is prop. This is propane. I have 1, 2, 3, 4 carbons, and you probably guessed that 4 is bute. This is butane. And here I've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. 8 is oct. This is octane. So far, so good? So far, so good. All right, so what if I throw in some double bonds, some triple bonds? If I have all single bonds, my name's going to end in ane. So when I looked at like this guy, assume those are all hydrogens. 1, 2, 3 carbons. 3 carbons is prop. 0 double or triple bonds. Everything is a single bond. It's going to end in ane. So this would be propane. But if I start adding in different kinds of bonds, if I have a double carbon bond, we're going to end in ene instead. So this is 1, 2. 2 is eth. This is eth. But because I have that double bond here, I'm going to call it not ethane, but ethene. So eth for 2 carbons, ene because I have a double bond. And if I have a triple bond, it's going to be an ine. I have 1, 2, 3 carbons. 3 is prop. This is propine. Propine. Ethene. This was propane. So far, so good? All right. Let's do some more practice. So 1, 2, 3, 4, 5. Count my carbons. 5 is pent. I have a double bond, so it's going to be pent-ene. Good. Pent because 5. Ene because of the double bond. Let's do this one. 1, 2, 3, 4, 5, and also a double bond. Again, we have pent because there's 5 carbons, ene because of the double bond. But my friends, these compounds are not the same. This double bond is between carbons 1 and 2. This double bond is between carbons 2 and 3. They're going to have different properties. They're different compounds. I cannot give them the same name. So we start throwing in some numbers. This guy right here, I'm going to call 1 pentene because the double bond starts on carbon number 1. This guy over here, I'm going to call it, you've probably guessed, 2 pentene because the double bond starts on carbon number 2. Figure out where that double bond starts, carbon number 2. This is 2 pentene. This is 1 pentene. So what's this guy? Is it 1, 2, 3? Is it 3 pentene? That would be a really good guess, except we have this other rule. We have to start counting the carbon chain closest to that end that has the special stuff, whatever that special stuff might be. These double bonds, that's a special thing, or later on we're going to talk about some functional groups. Those will be the special things. But for now, I have to start counting my carbon chain from the end closest to that double bond, which means that this is not carbon number 5. It's actually number 1. and this is number 2 and 3 and 4 and 5. And so I have again two pentene. These two molecules, I know it's really hard to see because I've scribbled all over them. Let me clean it up a little bit. So these two molecules, pentene and pentene, 2-pentene and 2-pentene, these guys are actually the same molecules. I just like spun them around. Because molecules are not flat on paper, they are three-dimensional objects that can spin around in space. So these guys are actually the same thing. They are both 2-pentene. Don't get fooled by molecules that are just flipped around a little bit. All right, so these compounds that I just mentioned, 1-pentene and our 2-pentenes, these are known as structural isomers. They have the same formula. If I count carbons, 1, 2, 3, 4, 5 carbons, there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Same thing over here. I'm going to have 1, 2, 3, 4, 5, 1, 2, 3 hydrogens, 1 hydrogen, 1 hydrogen, 1, 2, 1, 2, 3. That's a total of 10. All of these guys are C5H10, but they're not the same molecule. They are isomers of each other. They have the same formula, C5H10, but they have different structures, 1-pentene and 2-pentene. Because they have those different structures, they're going to have different physical properties. So far, so good? Good. So here are some more isomers. Both of these guys are C5H12. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Both of these guys are C5H12. They are very different compounds though, right? So this one is 1, 2, 3, 4, 5. 5 is pent. There are 0 double or triple bonds in here, so I'm going to end with an ane. This is plain old pentane. This guy, however, I have 1, 2, 3, 4 carbons in my main chain of carbons, and then I have this little branchy thing that has only 1 carbon. My branch of only 1 carbon, I'm going to call a methyl group. So I'm going to call this guy methyl 1, 2, 3, 4, 1, 2, 3, 4. 4 is bute, methyl butane. And I'm going to call it 2-methyl butane because the methyl group is on carbon number 2 of my butane main chain. How are we feeling about that? Good? Good. So before I flip away from these super cool isomers of each other, I'm going to ask you about the boiling points. Which one do you think has a higher boiling point? Which one of these two has the lower boiling point? They have the same masses because they both have 5 carbons and 12 hydrogens. Which one's going to have a higher boiling point, lower boiling point? Thoughts? If you thought that pentane has the higher boiling point, you are right. So boiling point of pentane is about 36 Celsius, and then for this 2-methyl butane, it's going to be only 28 Celsius. And the reason is this. We're still thinking about those electrons for those London dispersion forces, that intermolecular force, London dispersion forces. All these electrons floating around. Because pentane is kind of long and stretched out, there's simply more surface area for all of those electrons to have those London dispersion forces. Whereas in this guy, because of that branchy thing, it's a little bit more condensed. There's going to be a little bit less surface area, which means fewer spaces for those London dispersion forces to form. Good? Good. All right, so let's practice some more naming things. We talked about counting that carbon chain. We're going to look for the longest carbon chain, and be careful because sometimes it is not in a straight line on the paper. So our chains might take turns, go left and right, up and down. So not always in a straight line on our papers, but we're looking for the longest carbon chain that we can find. We're going to start counting the carbons from the end closest to the first functional group, and that first functional group might be a branch, like a methyl group or something like that, but it also could be the other functional groups that we're going to talk about later in this crazy long lecture. We're going to give numbers, assign numbers to our carbons that have those functional groups. When we fill out the final name, if there's more than one functional group, we're going to alphabetize them in the name. And then, of course, always checking for double bonds that will end in "-ine" and triple bonds that will end in "-ine". Are we ready? Get set. Let's name some compounds. So I'm looking for my longest possible chain. I can make 1, 2, 3. These guys would be branches, so they're not considered the main chain. They would be branches. I could do 1, 2, 3 and have those two as branches, but it looks like no matter what I do, I'm going to have 3 long in my longest chain. I have 1 branch, 2 branches. Each of those branches has 1 carbon, 1 carbon, 1 carbon, which means that each of these is called a methyl group because they each have 1 carbon. So I'm going to call this guy 2, 2, 2, 2 dash dimethyl, because I have di for 2 methyl groups and they're both on carbon number 2. Methyl group number 1, methyl group number 2, that's why it's dimethyl. 2, 2 because both of those methyl groups are on carbon number 2. What about the rest of the name? Well, if we go back to that main chain, there were 1, 2, 3 carbons, no double or triple bonds. 3 carbons is propane. So this is 2,2-dimethyl propane. I have 2 methyl groups, both on carbon number 2 of a propane chain. Good? Good. All right. So let's do another one. Let's do this guy. So I can count 1, 2, 3, 4, 5, 6. Or I can count 1, 2, 3, 4, 5, 6, 7, 8. Or I can count 1, 2, 3, 4, 5, 6, 7, 8, 9. This looks like it might be my longest chain. I can have 1 functional group on carbon number 4 and 2 on number 6. Or if I count backwards, if I go from right to left, carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a little bit better because now I have the 2 functional groups, those 2 branches, on an earlier carbon and the 1 on a later carbon. So it's just better, because there's just more here. How am I going to name this guy? So I have 1, 2 groups that each have 1, 2 carbons. So I'm going to call these guys ethyl groups. 2 carbons makes this an ethyl group. 2 carbons makes this an ethyl group. So I have 4, 4 diethyl. But wait, I also have an ethyl group on carbon number 6. So I'm going to call it 4, 4, 6 dash, how many ethyl groups altogether? 1, 2, 3, triethyl. And then my longest chain was 9 carbons long. 9 is non-ane. 4,4,6 triethyl nonane is the name of this crazy guy. All right, let's do some more. Let's count our carbons. 1, 2, 3, 4, 5, 6, 7. This is looking like it's probably our longest chain, but let's check just in case. I could also do 1, 2, 3. That's not as long. 1, 2, 3, 4, 5. Not quite as long. What about 1, 2, 3, 4, 5, 6, 7? I like this, but my branches don't start until carbon number 5. What if I did 1, 2, 3, 4, 5, 6, 7? This is also good. I've got 7, but I don't have any branches until carbon number 3, whereas when I did it this way, I had the branches on carbon number 2. And our goal is to always get those special things, the branches or the functional groups that we're going to talk about later, to have them on the earliest possible carbon. And for this example, carbon number 2 is going to give us the earliest options. So let me get rid of some of those extra numbers that we don't need anymore. Go back to 1, 2, 3, 4, 5, 6, 7. Perfect. So let's figure out what we have. This is a 1 carbon branch. 1 carbon is methyl. I have another 1 carbon branch. It's another methyl. I have, oh my goodness, another 1 carbon branch. It's another methyl. And here I have not 1, but 2, 1, 2, 1, 2 carbon branches. That's going to be 2 carbons as an ethyl. So far, so good? Good. So now I'm going to write my functional groups and how many of them there are and on what carbon numbers there are. So I could do 2, 2, because I have 1, 2, 2, 2, 3, because I have 1 methyl group on carbon number 3. I could do 2, 2, 3 trimethyl, and then I could do 3 ethyl, and I have 7 total carbons. That's heptane. This looks pretty good, right? Because I have 1, 2, 3, that's trimethyl. My 3 methyl groups are 2 of them on carbon number 2 and 1 of them on carbon number 3. And then I have an ethyl group right here, also on carbon number 3. But you know what we didn't do here? What we should have done? We need to alphabetize our functional groups. And right now I have something that starts with an M before something that starts with an E. And that's bad. So we're going to keep almost the same thing, except I'm just going to put this guy first because E comes before M, and then that guy's going to come next because M comes after E, and then we'll finish up with that same heptane. So we're just going to trade those 2 guys. So the better name for this is going to be 3 ethyl, 2, 2, 3 trimethyl heptane. Good? Good. All right. I'm going to get rid of some of those markings so that we can do another problem. All right. What about this guy? So we could do 1, 2, 3, 4, 5, 6. There's an option. We could do 1, 2, 3, 4, 5, 6, 7. That's better. I could do 1, 2, 3, 4, 5, 6, 7. I want to get my functional groups on the earliest possible carbon with my longest chain. So 1, 2, 3, 1, 2, 3 looks like a good option. Or I could do 1, 2, 3. This could be a good option. 4, 5, 6 is not as long as the 7 though, so I don't want to start on this side. So we're going to go ahead and start with carbon number 1. Let me get rid of those scribbles so that we only have 1 set of options left. So we're going to keep that 1, 2, 3, 4, 5, 6, 7. Good. So let me get rid of that 6. We don't need that one. So what do we have? We have on carbon number 3 a methyl group, on carbon number 3 an ethyl group because there's 1, 2 carbons. 2 carbons is ethyl. On carbon number 4 I have also an ethyl group. 1, 2, an ethyl group here. And then I have 1, 2, 3 carbons. 1, 2, 3 carbons. 3 carbons is propyl. So checking our alphabetization. Ooh, I don't know why I said that like that. I've got an ethyl. I've got a methyl. I've got a propyl. Who comes first? Ethyl does. So I have ethyl groups on carbons number 3 and 4. So we're going to do 3, 4 diethyl. Next up, should I do M or P? M. M's the winner. We have a methyl group on carbon number 3, only one of them. So 3, methyl. And then propyl group on carbon number 4. 4 propyl. We're almost done. How long was our longest chain? 7 carbons. Heptane. We did it. 3, 4 diethyl, 3 methyl, 4 propyl heptane. Brilliant. We're going to go ahead and put away those branchy things and look at some different kinds of functional groups. And the first one that we're going to look at is this thing called arenes, and these are phenyl groups. We call them cyclic, we call them aromatic, and they're basically just these rings. And they have alternating, and we'll talk about how this is not quite accurate, alternating single, double, single, double, single, double bonds. They're considered aromatic because they do tend to smell kind of sweet-ish. Lots of fruits tend to have these phenyl groups in their compounds. So we're going to call them phenyl somethings. Let's figure this out. So this example right here, I have 1, 2, 3 carbons. 1, 2, 3 carbons. And on carbon number 2, I have this phenyl group. So I'm going to call this guy 2-phenyl because the phenyl group is on carbon number 2. I have 1, 2, 3 carbons. That's prop. Meth prop is 3. I have a double bond, so it's going to end in ene, not ane. 2-phenylpropene. Good? Good. Let's look at this functional group, halogenoalkanes. Just a lot of letters to say we added some kind of halogen. Remember that halogens are those group 17 elements, fluorine, chlorine, bromine, iodine. So we used to have a hydrogen here, we knocked that hydrogen off and we replaced it with some halogen, fluorine, chlorine, bromine. So I'm going to count my carbons, 1, 2, 3. I have a chloro group on carbon number 2. So I'm going to call it 2-chloro. I have 1, 2, 3 carbons, meth, eth, prop, 2-chloropropane. Propane because there's 3 carbons, 2-chloro because I have a chlorine on carbon number 2. How about this crazy guy? I have 1, 2 carbons. That's going to be ethane, meth, eth. Meth, eth. I have 2 chlorines and 1 fluorine on carbon. We're going to alphabetize, and C comes before F, so I'm going to talk about my chlorines first. I have 1, 2 chlorines on carbon number 1, so I'm going to say 1, 1 dichloro. And then I have 1 fluorine also on carbon number 1, 1. Whoa, I didn't give myself enough space. Fluoroethane. 1, 1 dichloro, 1 fluoroethane is the name of that compound. Good. All right, one more. I only have 1 carbon. My prefix or my number 1 root is meth. There's no way to make double or triple bonds if you only have 1 carbon. And so it's going to be methane at the end. I have 2 chlorines and 2 fluorines. Chloro becomes before fluoro in the alphabet. So this guy is called difluoromethane. I do not have to say 1, 1 difluoro, 1, 1 difluoro, because there's only 1 carbon. So of course they're on carbon number 1s. We can ignore the numbers. Good? Good. All right, so let's look at alcohols. So alcohols are organic compounds that have a hydroxyl group on them. So I used to have an H here. I knocked that H off and I replaced the H with an OH. OH. This is a hydroxyl group. and it makes this compound an alcohol. And I'm going to use my same roots. So this compound right here has 1 carbon. My root for 1 carbon is meth. I have an OH group, which makes it an alcohol. We're going to end the name in -ol. So I'm going to call it methanol. This is methanol. This guy has 1, 2 carbons. 2 carbons is eth. Because it's an alcohol, that OH group is going to be ethanol. This guy has, so be careful, this line is pointing to the O, so there's not a carbon here. There's an oxygen here. There is a carbon here, there is a carbon here, there clearly is a carbon here. So I have 1, 2, 3 meth, eth, prop. This is propanol. Let's think about our numbers. So I clearly don't have to add a number to which carbon this OH is because there's only 1 carbon. Of course, it's on carbon number 1. I also don't have to add numbers here because if there's only 1 hydroxyl group, it's going to be on carbon number 1 because I'm going to count 1, 2. If the OH group was over here, I would count 1, 2. So regardless, we're going to have the OH group on carbon number 1. We can only have a 1-ethanol, and so I don't need to include the number. Propanol, though, I could put the OH group here instead of here. And so I should clarify that this is 1-propanol because I have the hydroxyl group on carbon number 1, not on carbon number 2. 1-propanol. All right, next up, we're going to look at aldehydes. So aldehydes, we have, so carbon is bound to an oxygen with a double bond at the end of the molecule. So we're only looking for double bond to an O, carbon double O, at the end of the molecule. And these are called aldehydes, and their names are going to end in al, which is different from the alcohols, but the OH, those ended in ol. So we're going to count 1, 2, 3, 4 carbons. 4 carbons, meth, eth, prop, bute. This is butanal, not butanol. Same thing here. Here's carbon number 1, carbon number 2, carbon number 3. Oh gosh, should I do carbon number 4 or carbon number 4, 5? Ooh, we should do 4, 5 because that's the longer chain. We'll get rid of that 4. So I do have a couple extra things on this guy. So there's this one, it's a methyl group on carbon number 3. And then we also have this chloro group on carbon number 2. So I want to know alphabetically who comes first, chloro or methyl. It's going to be that chloro. So I'm going to call this guy 2, because it's on carbon number 2, 2-chloro, 2-chloro, and then we're going to call it 3-methyl, 3-methyl. Back to counting my carbons, there were 1, 2, 3, 4, 5 carbons. That's pent. And because I have this double bonded O at the very end, I'm going to call it al. 2-chloro, 3-methyl pentanal. 2-chloro, 3-methyl, 1, 2, 3, 4, 5 pentanal, because I have this double bonded O at the very beginning of the molecule. Good? All right. So what if I have that double bonded oxygen, but it's in the middle, not at the end of the compound. Now, instead of being an aldehyde, aldehydes are at the, aldehyde. We have that double O at the end of the molecule. If it's not at the end, then it's not an aldehyde, it's a ketone instead. The name is going to end in -one instead of al. So here's an example, and these actually are the same two guys. So I have carbon, 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 H3, H3, just an O, H3, H3. So this carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. Whoa, that's an H, not a 3. But this carbon right now only has 1, 2, 3 bonds, and the oxygen only has 1 bond. So we have to have a double bond there to get everybody to that octet rule. So I have this double bonded O in the middle, which is exactly the same thing as what's happening here. I have carbon, 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 double bonded O in the middle. Since it's in the middle, it's a ketone. I'm going to count my carbons, 1, 2, 3, meth, eth, prop. Prop is my root for 3. It's going to end in -one. So this is propanone. This is propanone. It is more commonly known as acetone. So propanone is the same thing as acetone, also known as fingernail polish remover. So this is the stuff that gets fingernail polish off of your nails. Let's do this crazy guy. So this is kind of a crazy thing. I talked about that double O not being at the end of the molecule for a ketone. I'm going to call this carbon number 1, which kind of makes it like the end of the molecule, except it's bound to a phenyl group also on carbon number 1. So it's not exactly the end of the molecule. So I've got a phenyl group on carbon number 1, and I also have my carbonyl group on carbon number 1. Carbon number 2, 3, 4, 5, 6, 7, 8. There is a carbon here, but I don't count it as part of the chain. I count it as the phenyl group. So don't count that first carbon in the phenyl group as part of your chain. So what do we have? I have 1 phenyl, because I have this phenyl group on carbon number 1, and then I have 1, 2, 3, 4, 5, 6, 7, 8. That's oct. And I have my double bonded O, and so I'm going to call it 1-one to let us know that that double bonded O is on carbon number 1. 1 phenyl octan 1-one. Kind of weird to throw the number into the middle of the name, but we do it actually often in organic chemistry. We're just cool like that. All right, so the next functional group that we're going to look at is carboxylic acids. Carboxylic acids have these carboxyl groups. Carboxyl groups are going to have a C, a double O, and an OH. That C double O is a carbonyl group. The OH, like in alcohols, is the hydroxyl group. And when I put those two together, we get the carboxyl group. Carbonyl plus hydroxyl, carboxyl. So this is known as a carboxyl group. COOH, COOH, carboxyl group. And these guys are known as carboxylic acids. And how we name them is we count our carbons, and then the names end in oic acid. So here I have carbon number 1, 2, 3, 4. The carboxyl group always gets carbon number 1. So carbon number 1, 2, 3, 4. Meth, eth, prop, bute. This is butanoic acid. Butanoic acid. Good? Oic acid. This crazy guy here, carbon number 1 is here. Carbon number 1, 2, 3, 4, 5. I have my carboxyl group here, makes it that carboxylic acid. I have a methyl group here on carbon number 1, 2, 3, 4, 5. So methyl group on carbon number 4. And then we also have this phenyl group on carbon number 3. So I'm going to call this guy, M comes before P, so I'm going to call it 4-methyl, 3-phenyl, and I had 1, 2, 3, 4, 5 pentanoic acid because it's a carboxylic acid. 4-methyl, 3-phenyl pentanoic acid. Good? Good. This guy is super easy. There's only 1 carbon. That's meth. This is methanoic acid. That OOH makes it that carboxylic acid, methanoic acid. All right, just a few more functional groups to go, my friends. We are making some serious headway here. So esters. Esters are pretty cool. There is a carbon double bonded to an oxygen and also single bonded to another oxygen. These are almost like carboxylic acids. It's kind of like, imagine that there had been an OH here. So I had C double O, OH, but then we knocked the H off and let all of this other stuff take its place. So we're going to use that actually to figure out the name. So all the stuff that replaced the hydrogen in the hydroxyl group, all of this is going to get named first. And we have 1, 2, 3, 4, 5 carbons. So I'm going to call this pentyl because of those 5 carbons. And now I'm going to figure out how many carbons do I have on the other side. I have 1, and there's that 1 too. So I'm going to call it S and O8. O8 is how we end these ester guys. Pentyl, because I have these 5 carbons here. Ethanoate, because I have 2 carbons on this side. Double O to a single O. Pentyl ethanoate. Let's look at this one. COO, imagine there used to be an H there, but we knocked it off and replaced it with CH3 instead. Only 1 carbon makes it methyl. Over here, I have 1, 2 carbons, that's an F. So I have methyl, that 1 carbon where the H used to be in the carboxylic acid group, and then I have F because of 1, 2 carbons, F and O8. O8 because there's that double O and then a single O. That's an ester group. I'm going to get rid of those scribbles so that you can see it. This right here tells us that it's an ester. Good. Carbon, double O, single O, and then more carbons. So if I take away that double O, and I only have 1 O that is single bonded between 2 carbons, this is no longer an ester, it is now an ether. So I have some carbons, and then I have an oxygen, and then we have some more carbons. These are ethers. We're going to just pick the shorter chain. We're going to write it first, and then I'm going to use the word oxy in the middle. Then we're going to name the longer chain. So this one I think is pretty easy to name. So I have 1, 2, I have 1, 2. There isn't a shorter chain or a longer chain. They are the same in length. So I'm going to start with either one is going to be S. So we're going to call it S. And then that O in the middle is going to be oxy. And then the rest of it is ethane. Oxyethane. Tells us that I have 2 carbons and then an oxygen and then 2 more carbons. Over here, same idea. I have 1 carbon and then I have 1, 2, 3 carbons. This is meth, eth prop. We start with the shorter one first, so I'm going to call it meth, and then oxy for that O, and then 1, 2, 3 propane, methoxypropane. No double bonded O's in here, my friends. So we're looking at just that 1 single bonded oxygen between those 2 carbon chains. We name the shorter one first, oxy, and then the longer one next. I think these are actually easier to name than a lot of the other guys. All right, so now we're going to go away from our oxygen groups and we're going to look at some nitrogen groups. We have amines, and then the next one is going to be amides. So with amines, we have a single bonded nitrogen, and then the name is just going to end in amine. So often, but not always, often these 2 R's, and the R stands for radical groups or side groups. It can be anything. Anything can be there. With our amines, often, but not always, we're going to have 2 hydrogens here. But there could be other stuff as well. So I'll go back to this where you can see under all the scribbles, my goodness. So naming this one first, I have 1 carbon. 1 carbon is meth, it's going to end in amine. Methamine is what this is. If I look at this guy, find my longest carbon chain. 1, 2, 3, 4, 5. Be careful. This is carbon number 1, 2, 3, 4, 5. So I'm going to have my amine group on carbon number 2. I have 5 total carbons. So I'm going to call it 2-pentamine. Pent because I've got 5 carbons. 2 because the amine group is on carbon number 2. Let's do this one over here. So I have 1, 2, 3 carbons, no branches. It looks like this NH2 is at the end, so that's super easy. Meth, eth, propamine. And we should clarify that the amine group is on carbon number 1. Good, good. So amides are similar to amines, except now I'm adding a double bonded O. So if I had NH2 to carbon, it was an amine. But if I add a double bonded O onto that carbon, it's now an amide. How I remember that? Amino, there's literally no double O. Amidos do have a double O. Pretty easy to remember, right? No double O, they do have a double O. Let's name these guys. So I have 1 carbon, 2 carbons. I'm going to call this guy meth, eth, ethanamide. Ethane for those 2 carbons, amide, ethanamide. Let's look at this guy. I have carbon number 1, 2, 3, 4, 5. Pent for the 5 carbons, amide because we have that amine group, pentanamide. One more, carbon number 1, 2, 3, 4, meth, eth, prop, butanamide. And again, remember, because I have this double O here, so we have nitrogen, carbon, double O. This makes this an amido group. If I instead, if we did not have that double O there, it would not be an amido, it would be an amino, and we would name it with amine instead of amide. Good? All right, we are so close, my friends. We're getting there. Let's talk about these nitriles. So nitriles come in cyano groups, kind of cool. So cyano group is carbon triple bonded to a nitrogen, and this is going to be at the end of the molecule every single time. This can also actually, interestingly, be a polyatomic ion. So we can have CN is cyanide. If we're talking about our polyatomic ions, cyano group, nitriles if we're talking about organic chemistry. So we're just going to name these guys similar to how we named our amides. So count our carbons 1, 2, that's going to be ethanitrile. And then I have carbon number 1, 2, 3 here, meth, eth, prop. So it's going to be propanitrile. Sometimes you might hear people say propionitrile, but it's the same kind of dealio. We have on carbon number 2 a bromo group, so 2-bromopropanonitrile. One more. I have carbon number 1, 2, 3, 4, 5. So it's going to be pentenitrile. Because I have that double bond, but I need to clarify that it's in carbon number 2. So I'm going to throw a 2 in there. So pent-2-enitrile or 2-pentenitrile, because that double bond on that carbon starts at carbon number 2. Good? Good. All right. Let's practice those functional groups that we just learned. My friends, we're so close, like 5 more minutes. We got this. So aspirin molecule here, this is also known as acetylsalicylic acid. I want to know what functional groups do you see? Hopefully you see carboxylic acid group. We've got a carboxyl group here. which is kind of like a carbonyl and a hydroxyl combined. Carboxyl group is here. I have a phenyl group here. Here's a nice phenyl group. And then here we've got carbon double O and a single O. This is an ester. And then over here we've got a methyl group. Good? Good. Let's do another one. So this is pseudoephedrine, found in like Sudafed. It's really good for when we have colds, clearing our sinuses. What functional groups do you see? I see methyl group, methyl group. Up here we've got hydroxyl group, makes this an alcohol. I have N, but there's no double O, so this is going to be amino, not amido, because there's no double O bonds next to the nitrogen. And then over here, we've got yet another phenyl group. Good, good. All right, so we are done naming things mostly. We're going to talk about classifying compounds, which is way easier than all the naming stuff that we've been talking about. So compounds will react differently based on how many carbons the carbons are stuck to. So what we like to do is actually count how many carbons are bound to the carbons, and that allows us to classify these compounds. So primary carbons are bound to only one other carbon atom. So if I'm looking at this carbon right here, it's bound to only one other carbon. It's going to be a primary carbon. This carbon, however, let me pick a different color. This carbon is bound to two carbons. That makes it secondary. This guy's a secondary carbon because this carbon is stuck to two other carbons. This carbon right here is bound to three carbons. That makes it tertiary carbon. This guy way over here, this guy is very special. It is bound to one carbon, two carbons, three carbons, four carbons. That makes it quaternary. Good. So again, we care about this because these compounds will react differently depending on how many carbons they are stuck to. We can also classify our halogenoalkanes by the same method, basically. So primary, secondary, tertiary halogenoalkanes. So a primary halogenoalkane, we're going to find the halogen, find the carbon that it's stuck to, and then find out how many carbons that carbon is stuck to. So, my picture did some weird things. So my bromine is here. Sorry, my bromine is here. It is stuck to a carbon that is stuck to one other carbon. That makes this primary. If I have my bromine here instead, this bromine is stuck to a carbon that is stuck to two carbons. This guy is secondary. Here, again, my bromine got lost. I've got my bromine here. This bromine is stuck to a carbon that is stuck to only one other carbon. And so even though there's lots of branches in here, this bromine is still only primary because the bromine is stuck to a carbon that is stuck to only one other carbon. The other guys are H's, not carbons. Last but not least, I've got this bromine down here is bound to a carbon. This carbon that's stuck to the bromine is stuck to 1, 2, 3, 1, 2, 3 carbons. That makes this a tertiary halogenoalkane. We can do the same thing with alcohols, and it's super important for us to be able to classify alcohols because we're going to look at a couple different reactions that they go through, and it depends on if they're primary, secondary, or tertiary, what we can do with them. So let's draw these guys out. So 2-propanol, remember that meth-eth-prop, prop means that we have 3 carbons. So 1, 2, 3, meth-eth-prop. I'm going to put my alcohol group on carbon number 2. Alcohol is OH. We're going to fill everything else in with the hydrogens that it needs. So lots and lots and lots and lots of hydrogens so that carbon has 4 bonds all the way around. So I'm going to look at that hydroxyl group now, find my alcohol group, that hydroxyl group. It is bound to a carbon that is bound to 2 other carbons. So this one's going to be a secondary alcohol. Let's do the same thing with the next one, 2-methyl-2-propanol. I'm still going to start with my prop, meth, eth, prop. I'm going to put a methyl group on carbon number 2. Remember that methyl groups are 1 carbons with lots of hydrogens around them. I also have 2-propanol, which means that my hydroxyl group is also on carbon number 2, just like that. Then we'll fill in everything else with the hydrogens that it needs to get to those 4 bonds around each carbon. Now let's find that hydroxyl group. It's here on carbon number 2. Carbon number 2 is bound to 1, 2, 3 carbons. The hydroxyl group is bound to a carbon that's bound to 1, 2, 3 other carbons. That makes this a tertiary alcohol. Last one more. You can probably guess that this guy is going to be primary, right? So 1-propanol, meth, eth, prop. We're going to put the hydroxyl group, the OH, on carbon number 1. Everything else is going to be a hydrogen. Fill in all those bonds. I'm going to find that hydroxyl group one more time. It's here on carbon number 1. It's bound to a carbon that is bound to only 1 other carbon. These other guys are hydrogens. So this one is primary. So amines can also be classified based on how many carbons their carbons are bound to. So this nitrogen is bound to a carbon that is bound to 1, 2 other carbons. It's secondary. This nitrogen is bound to this carbon, and there's actually 2 methyl groups, so CH3 and CH3. So this nitrogen is 1, 2, 3 carbons. It's a tertiary amine. This nitrogen is bound to 1 carbon, 2 carbons. It's another secondary amine. And I have never, ever seen IB ask us to name amines that have multiple functional groups on the ends, multiple carbon chains on the end. But just in case, phenylamine is this guy. NN is telling us that I have 2 di for 2 methyl groups. 2 methyl groups are both on the nitrogen. That's these methyl groups. There are 2 of them that are both bound to the nitrogen. Butan 2 amine 1, 2, 3, 4. There's the bute. The nitrogen is stuck to carbon number 2. So this guy is this guy, which means that this one must be this one. So I have a methyl group on one side of that nitrogen. So nitrogen has a methyl group. And then there's 1, 2, 3, 4, 5 carbons. There's the pent. Because this nitrogen is stuck to carbon number 2, it's going to be 2-amine. We did it. An hour and 2 minutes, but we did it. We defined homologous series. They're like methane, ethane, propane, butane. They're in the same series that we're just throwing on longer carbon chains. We talked about structural isomers. Those are the guys that have the same formula but different shapes. We talked about functional groups. There are so many of them. That's why you have flashcards. We talked about those classes of organic compounds. Those classes depend on the functional groups. We talked about how to name things. Those names also depend on those functional groups. And also we talked about classifying organic compounds, primary, secondary, tertiary, depending on how many carbons the carbon is bound to. Good work.